Hello, thank you everyone. So I will talk about the QUMIN project, which was funded by the Manutech-SLEIGHT, and which is part of a bigger project, so led by Stéphane Avril. And so my focus on this project is on currently on the mechanical characterization of hydrogels. The main application, the idea, is to focus on vascular aging. As you probably all know, the European population is aging and quite fast. And one of the problems in aging is the vascular aging and the smooth muscle cells, which are the cells that are responsible for the contraction of the arteries in response to the change in pressure and to the heartbeats. These cells, they can change their behavior, and notably they can take over behavior, behave like, for example, bone cells, or they can become senescent cells, which are basically aged cells who don't behave normally anymore. One of the issues is that the arteries, which are normally elastic, which are able to deform, become too stiff, cannot deform, and that creates a lot of pathologies. So the team has worked on this topic for a few years. And for example, we've developing numerical models at the organ scale to mimic the behavior of arteries and to try to predict some outcomes and incorporate some patient-specific data. And a bit more recently, we've switched to the cell scale to understand how cells behave and how they age, particularly. So the question is, can we rejuvenate the cells? The idea is, if we take an old cells, can we rejuvenate so that it works again like young cells? So to achieve this, the project is separated in 4 main parts: the in vitro and in vivo models, the spatial transcriptomics, so to get an idea of the gene expression, 4D strain mapping, so 3D plus time, and numerical modeling. And my part is mainly in the in vitro models and also on the 4D strain mapping. And so, as I said, it's something that was started already in the lab. And the first studies focused on 2D models. So the smooth muscle cells, the main cells of the arteries, the ones that are really our topic for today, they are seated on 2D gel, so hydrogel with different stiffness, and the cells are lying on top of the gel. These gels, they contain fluorescent beads, and by imaging with confocal microscopy, you can measure the displacement of the beads when you remove the cells, and that will give us an idea of the basal contraction force exerted by the cells. And then you can compare the effect of young versus aged cells and see how cells respond to different stiffness of the substrate. Now, this is really good, but in vivo, these cells, they are not in 2D, they are not lying on the substrate, they are incorporated in a 3D matrix surrounding them. So the idea now is to take this to the next step by creating this in vitro model in 3D. And so this is my work. So this is in 3 parts. The first is to find these 3D models that are suitable for our cells. Once we have identified some models, we need to characterize these models. And by mainly also doing TFM, so the ultimate goal is traction force microscopy to quantify this traction force generated by the cells. And then the last part is the phenotypic characterization, because these cells, we know they can change their behavior, they can behave like other cell types, so we want to be sure that in our model we are working with the right cell type. So for today, I will focus on the first 2 parts, so the selection of the model and the different imaging method we developed in the lab, with a focus on the OCT imaging. So for the first part, the model, so selecting hydrogels that are suitable for the 3D encapsulation of the cells. I decided to work with hydrogels that are collagen alginate interpenetrating polymer network, because collagen provides the support for cells. Cells can bind to collagen, they can remodel the collagen, so it's their biological support. while alginate is biologically inert, so the cells cannot bind to alginate, they cannot degrade it, but it's very useful to tune the mechanical properties of the hydrogel. It's much easier to tune the properties of the alginate than the collagen. So by doing this, I have hydrogels that are suitable for cells and that I can control the mechanical properties, which is very important for us because we want to see how cells will respond to different mechanical environments. And also, these gels are extremely easy to fabricate because basically we're just mixing everything together and putting in the incubator to cross-link. This is what the smooth muscle cells look like. So you have what cells will look on 2D. So they are quite spindle-shaped cells, very thin. And you can see in 3D, it's even more exaggerated, these very long and thin cells, which is actually what we would expect them to look like. So we're validating our hydrogel. We found a suitable composition. Cells remain alive for a few days, and they have the desired morphology. So now that we have our hydrogel, we can move on to the next step, which is finding the suitable imaging method. The traditional method to image cells in the hydrogel is confocal microscopy. And you would stain cells with fluorescent markers. And if you want to do traction force microscopy, you can put these fluorescent beads in the gel and track the displacement of these beads. The problem with this method is that you're exposing cells to the laser, which can damage them in the long term. And the imaging part is very slow. So if you are trying to image a dynamic process, if you want to see how your cells will contract under a certain stimuli, this method is not suitable. So we tried to work with other methods, find a compromise between reducing the sensitivity of the method and the resolution and increasing the speed. And one method that we're currently working on and that is quite promising is OCT, so Optical Coherence Tomography. This is what our setup looks like. So you can see that we're placing the hydrogel in a small mold to image, and the OCT will give us cross-section. So OCT is an interferometry techniques, so it's based on the light interference. And we can see through the thickness of the hydrogel, we can see through about 0.5 millimeter thickness. And we need to use imaging solution because if we image in air, we are decreasing the resolution. And also, since I work with hydrogel, I need to maintain them hydrated, so I need an imaging solution. The idea is to use a setup that has been developed by QUMIN, which is a startup that has been made from the work of the team. And we are combining the macroscopic mechanical characterization of the hydrogel with the tensile test, uniaxial or biaxial, we have both setups, with the microscopic characterization, which is based on the OCT images. So the idea is to perform the tensile test under the OCT and then to use digital volume correlation to go back to the local mechanical properties of the hydrogel. So the first step for my gel was to find a suitable imaging solution. We have quite a lot of different solutions now in the lab, and the best solution depends on the refractive index of the material and the thickness, also the density of your material. For my part, since I work with hydrogels, so there are something like 99% water, without surprises, the best solutions were the water-based solutions, and notably the Krebs ringer solution, which is just salt solution, which very conveniently is also suitable to maintain cell viability while I do the images. So now that I selected the image, the solution, and I can image my gel through the this 500 micrometer thickness. So what you see here is like slice of the gel. The next step is to validate that we can indeed track displacements with this method. So the first step is to perform what we call the rigid body motion. So it's just a translation of the field of view. So you image the field of view in the gel, and then you just translate this field of view. So you have no deformation. And we tried with large displacement of 200 micrometer and smaller displacement of 20 micrometer. Then we use a software for digital volume correlation. In our case, we work with Davis. We estimate the displacement for each set, and we can see the error of displacement between what we measure and what we imposed. And then we can select the optimized acquisition parameters with the OCT and the optimized analysis parameters with the software. So the principle of DVC, the principle is actually quite simple. You will cut your volume into smaller subvolumes, and for each volume, each of these subvolume, you will track this subvolume between the reference image and the deformed image. And this will give you the displacement for each subvolume. Now, to do this, you have a lot of options. First, you can select the size of the subvolume you want to work with. You can select the peak radius, so you can tell the algorithm how far you expect the subvolume to be in the deformed image. You can change the shape of the subvolume, and you can change the overlap between all this subvolume. So you can imagine it's a really large set of parameters that you can move all of them independently. So it's quite a lot of work to analyze the best sets of parameters. And that's what one of the interns did. So you can see for the large displacements, 200 micrometer, I'm plotting here the measured displacement with different protocols, different sets of parameters. And what you can see is that it's extremely sensitive to the algorithm, so to the sets of parameters. With some parameters, we can get extremely good measurement, very accurate, and while with some parameters, we're extremely far from what we applied. And now for the small displacements, we did not manage to reach the correct displacement. We always have some offset, and we're still trying to work on it to understand if it's something we can fix by still playing with the parameters, or if it's just with this type of image, we don't have enough information in the image to get correct measurement. We also evaluated another image analysis method, which is image registration. And in this case, the algorithm works much more at a global scale. It's a quite same principle, trying to fit the deformed image on the reference image and computing the displacement that you need to apply on the image to reach this correlation of the image. And in this case, we could get extremely good results. As you can see in the hydrogel part for the translation, we get something that is very accurate. Now we still have some questions on larger displacement and other deformations, but it's very promising because we can get very close results. So it's validating the first step of tracking the displacements in the image. The next part is to perform the tensile test under the OCT. Now, I work with hydrogels that are extremely soft. And by extremely soft, I mean something around like 1 kilopascal for the elastic modulus. 1 kilopascal, basically, you cannot handle it in the hands. The gel will just be smushed between your fingers. So I can't take the gel out of the mold and place it in the clamps like I would do for any other material, because my gel would just be smushed between the clamps. So we decided to kind of mold the gel around clamps so that we don't have to handle the gel. It's a very promising idea, but also much more challenging than what we expected, of course. I don't know why I'm still surprised after all these years, but we thought it would be quite easy. We had a lot of leak issues with the molds, some of the design issues. And now, as you can see on the last image, we still have some issues that the gel will slip around the grip when we are applying the displacement. And also, because the gels are extremely soft, the forces that are measured when I deform the gel are extremely low. And even with the 1 Newton load cell, we're in the range of the noise. And so because the load cell is so sensitive, just the acceleration of the motor, the acceleration of the displacement is perceived as a force by the load cell, which is in the range of what we're applying right now. So we're still working on adjusting the geometry to increase the cross-section of the gel, so we can be above this noise that the load cell feels. And we hope also that if we increase and we change the geometry, we can also improve the adherence between the grips and the hydrogel. So to conclude, we have a promising method here to be able to characterize the hydrogel. Because with the OCT, we can have the non-invasive and marker-free imaging of the hydrated hydrogels. I think it's very important to stress it here. we're imaging the hydrogels in their hydrated form, which is very difficult to perform with hydrogels. And in my hydrogels, you can see that I don't have much porosity inside, which is itself an information, but we've worked with other people and they have much larger porosities in the hydrogel, and you can see them with the OCT, so you can characterize also the structure of the hydrogel, and you can see under deformation how the structure will change. And with this method, we can track the displacements that are at the cell scale, which is very interesting for us because it means that if we put cells in the gel, we can know what cells feel directly around them. We have access to the local behavior, not just the bulk behavior of the gel. And also, if we want to perform traction force microscopy, we know that we can reach a scale that is really relevant to the cells. Now, we still need more work because we need to adjust the setup and the loading protocol to adjust it to the very, very soft hydrogel, but it's already working for hydrogel that are stiffer. So we have something that works now. If, in any case, if you're interested, just let us know. And the ultimate goal for me is to evaluate the heterogeneities in my hydrogel so that I know what cells feel, and then I can measure the traction forces that are generated by my cells in these hydrogels. And I thank you for your attention.
Thank you, Sarah, for the presentation. Is there any question for Sarah about the QUMIN project? Please.
Okay, I'm not in that field, but anyway, I raised the question regarding collagen. I imagine, or I think to know that there's many types of collagen. So what are different families that can be measured with your setup?
So the collagen right now, what we use is collagen 1 from bovine skin, I think. It's very common. Most of the hydrogels, when people work with collagen, it's collagen 1 from beef or rat, very common because they're very easy to work with and to make hydrogel. And so collagen 1 is the most important collagen for the body. You can have also collagen 2, which is very important for our cartilage. We have some people who work with, I don't know if they incorporated collagen 2, but they are working for cartilage application, and they can also image your hydrogel. But basically, you can image a very broad range of hydrogel. It works also on tissues. The difference with tissues is that they are much more, are very dense. So the light penetration is quite limited compared to what we have with the hydrogel right now. But it also works. We have people working with endometrium, that works. We tried also some more like exotic application. We try to image mozzarella. It works also. Same, it's a bit dense, but you can image this. So it works on a very broad range on the hydrogel. The difference that you will get is how dense the material is. And then we need to adjust the immersion solution. But now we can cover quite a broad range of refraction index. So usually we manage to find something that is suitable for the gel.
I had maybe a brief question before we pass to the next speaker. So in a way, I mean, in the system, you measure the displacement of the material rather than this, the displacement of the cells. Did I get it right?
Yes.
Okay.
Yeah, so the idea is that you measure the displacement of the material around the cells. And based on this, when you know the mechanical properties of the hydrogel, which is why also I need to measure the local properties of my gel, then you know to have this displacement, the cell must have generated a force of this level. And this is what we want in the end, is to have to map the forces like this generated by the cell. So that's why we measure the displacement of the matrix around the cells.
Thank you. Thank you very much for the clarification as well. Okay, join me in thanking again Sarah